Alright, so this is going to be a video about related rates, and I think the best way to teach related rates is just to kind of solve a problem, just to kind of show you how these problems work. Okay, so this example, it says you are inflating a spherical balloon at a rate of 7 cubic centimeters per second. How fast is its radius increasing when the radius is 4 centimeters? Okay, so the first thing that we're going to do is we're going to translate everything from English to math so we have some equation to kind of work with. So the first thing it says you are inflating a spherical balloon. Okay, that's important to know that the balloon is a sphere. Okay, and then it's at a rate of 7 cubic centimeters per second. So what I'm going to do is convert this into some kind of variable. Now if you notice it says rate right here. Now anytime you see rate, think derivative. In this case it's going to be the derivative of volume with respect to time. So I'm just going to write dv over dt. Okay, so it's the change in volume over the change in time. In this case, it would be 7 cubic centimeters per second. Okay, so that's our dv over dt. And then it says, how fast is its radius increasing? So how fast is its radius increasing? We're not looking for what is the radius, we're looking for how fast the radius is increasing. So that means it's a rate. So it's the rate at which the radius is changing, or in this case, how it's increasing. So if we're looking for how fast that is, I'm just going to write dr over dt equals question mark, because that's what we're looking for. So we're looking for this rate at which the radius is changing when the radius is 4 centimeters. So I'm going to write a little at symbol here. At the radius is equal to 4 centimeters. So basically I just wrote down everything that I have here that's in this problem. I just basically translated it into math so that we can use it in some kind of an equation. Okay, the next step that you're going to want to do after you wrote down everything and you translate it into math is you're going to want to write an equation that relates this v and this r. So it's really similar to the implicit differentiation problems that we did earlier. We're basically going to be making an implicit differentiation equation, or just basically making an equation out of these. In this case, the v and the r are related by the volume of a sphere equation, which is going to be v equals 4/3 pi r cubed. Okay, this relates the v with the r. So we have the v and the r right here for this sphere. Now in order to get this dv over dt, I'm going to differentiate both sides of this with respect to t. So on the left side we'll have dv over dt, and then on this side we're going to have d over dt of the 4/3 pi r cubed. Okay, this value right here we actually know because it's right here with 7 cubic centimeters per second. So I'm just going to actually write that in there. 7 cubic centimeters per second. Just like that. From here, I'm going to take the derivative of this right here with respect to t. Okay, so what you're going to want to do, if you remember your implicit differentiation rules, the r and that t do not match. So what I'm going to do is I'm going to have to multiply a dr over dt at the end of this. So first we're just going to take the derivative as normal. So we're going to bring the 3 down and use power rule. So it's going to be 3, and this divided by 3 cancels. So you're going to be left with 4 pi r squared. So you're going to minus 1 from that power and get r squared. And then we have to multiply by dr over dt because that r does not match this dt. If you remember the video on implicit differentiation, it kind of explains where this whole thing comes from. Okay, so now we have all of this right here. Now, next step is you're going to want to try to figure out what other variables we can substitute in for. If you notice we substituted this dv over dt right here, we can also substitute this r right here because the r right is equal to 4 centimeters. So I'm going to write that in here. And we end up with something like this. Now this dr over dt right here, that's actually what we're trying to solve for. So this is what we're going to be solving for. And if you notice there's no other variable, so this kind of works out nicely. We're going to actually be able to solve for this dr over dt. So the next thing I'm going to do is simplify all of this, namely this side right here. It's 4 centimeters squared. So this is a squared right here. So it's going to be 4 centimeters times 4 centimeters, which is 16 centimeters squared. So I'm going to write that in really quick. Now to solve for dr over dt, I'm just going to divide both sides by 4 pi times 16 centimeters squared. So this is going to cancel. What you do to one side, you equally have to do to the other. Okay, now we have centimeters cubed divided by centimeters squared here, so I'm going to cancel out 2 of these, so the centimeters squared are gone, and then you're going to be left with just this centimeters per second for this dr over dt. Okay, so right now we have 7 over 4 times pi times 16, so I'm going to simplify that over here. Now, since this is a real world problem, you can't just keep it in terms of pi like this. You're going to want to just kind of get a decimal approximation for this. Just throw it in your calculator and you should get 0.035 centimeters per second for your final answer. So this is how fast the radius is increasing when the radius is 4 centimeters for this balloon that's being blown up. So that's related rates. If you have any questions about anything in this video, let me know.